Hello everyone, today let's just take a look at QP102. We're just going to be looking at the discrete uniform distribution here. So we're just rolling a fair-sided die one time, so this is as basic as it gets. Let's find the average or expected value of x first. So we know the definition of expected value. We're going to sum up over all the possible values that x can take times the probability that that x occurs. And x is uniform obviously because it's a dice roll, so the probabilities for each of these are going to be 1/6. So our expected value is just going to equal 1/6 times the sum over all of our x's. So we know the sum of the first 6 integers is just going to be 6 times 6 plus 1, which is 42 on 2, is going to be 21. So this is going to give us 21 on 6, also known as 3.5. Okay, so that was pretty simple. Now let's do the variance down here in part B. So we know variance is equal to the expected value of the square difference between x and the mean. So when we take that expected value, we get something like this. We know that the probability that x equals x, again, is 1/6 for all x. So we can pull that out front. Now let's calculate all of these values. The difference between 3.5 and 4 is 1/2. The difference between 5 and 3.5 is 3/2. The difference between 6 and 3.5 is going to be 5/2. Now when we square all of these, I'm going to get 1/4 here, I'm going to get 9/4 here, and I'm going to get 25/4 here. And now these are the square differences between the mean for 4, 5, and 6, but you notice that for 3, 2, and 1, they're going to have these same distances, right? So we can just add these up and then multiply them by 2. So that's the value of this inner sum right here, so we still have to multiply it by 1 on 6, and when we do that, it's going to cancel with this 2, and we're going to get 1 on 3 instead. Now we can distribute this 1/3 inside, and we're going to get 1 on 12 plus 9 on 12 plus 25 on 12. When you sum up the numerators, that's going to give us, well, 34 plus 1, 35, and then on the bottom we have 12, so this is going to be our variance. So we expect the value of one dice roll to be 3.5, and we expect the square distance from the mean to be 35 on 12. But the problem with variance is this is in terms of squared dice values, which is kind of hard to interpret. So for that, we can pull out the standard deviation. So the variance is in terms of square units. So if we just take the square root of the variance, we take the square root of 35 on 12, well, that will give us our standard deviation. And when we do that, we get 1.7. And this is going to be easier to interpret because it's not in squared units anymore. It's just in terms of normal dice value units. So this right here tells us that on average, we expect the number of dice pips away from the mean to be 1.7. So now to calculate the probability that a roll falls within one standard deviation of the mean, well, this right here is one standard deviation, 1.7. So now all we want is the probability that x's difference from the mean is going to be within one standard deviation. So I can expand out the absolute value like this and add 3.5 everywhere, and then I'm going to get a 5.2 as my upper bound, and I'm going to get a 1.8 as my lower bound. Now the probability of a random roll being between 1.8 and 5.2, well, x is a discrete, so it can only take integer values, so that's just equal to the probability that if we round down here and we round up here, equal to the probability on any given roll that x is between 2 and 5. So we know how to calculate that, right? There's 6 values on a dice. The probability that's between 2 and 5, well, that makes up 4 out of the 6 possible options. So our answer is 2/3. So this just means that 2/3 of the time when we roll the dice, we expect it to be within one standard deviation, which is very similar to what we see in the normal distribution. But now if we just add one more part real quick, let's answer the question, how many standard deviations is 6 away from the mean? So I got x equals 6. Okay, I'm 2.5 units of dice value away from the mean. But the z-score is saying, okay, you're 2.5 units of dice value away from the mean, but how big is that relative to the average value away from the mean? Okay, so we know that our average distance from the mean is 1.7, our standard deviation, and we're saying what multiple of that standard deviation z is equal to the number of units away that you are, which is 2.5. Then obviously we can solve for z. It's just going to be equal to 2.5 on 1.7, and that's going to be 1.47 roughly. Now notice that the number 2.5 was obviously in units of dice value, and so is the number 1.7. So when we divided one by the other, we kind of got rid of units. So this z-score here is a unitless number, which means it's standardized. So that means I can interpret this z-score without even knowing what the underlying distribution is, right? If you just told me that some sample from a random distribution had a value of 1.47 for its z-score, well, then I would know that that's abnormally high because the standard deviation is 1, obviously, right? So I know it's 1.5 times a normal standard deviation. Versus if I didn't know your distribution and you told me that some value you sampled was 2.5 units of dice value away from the mean, well, I'd have no idea what you're talking about because I have no idea of what the spread is in your distribution. So I wouldn't know if this is abnormally high or abnormally small, versus with this, I know that this is abnormally high because it's bigger than one standard deviation away. So that right there is the power of z-score and standard deviation. It just gives you a way to standardize the spread that you're talking about in your distribution.